Welcome to chemistry classes. In this video, we are going to discuss about coordination compound. Day 12 chemistry chapter coordination compound. Okay, here we learnt already transition metals. Transition metals join with a different type of molecules, negatively charged molecule or neutral molecule, and it form coordination compound. Transition metals make bond with neutral molecule or negatively charged particles form coordination compound. Neutral molecules mean here transition metals such as nickel or cobalt or copper. It make bond with neutral molecule H2O, NH3, this type of neutral molecule, or it will make bond with negatively charged particles, negatively charged species such as Cn minus, Cl minus, OH minus, and form coordination compound. Okay, here you have some example for coordination compound. Here chlorophyll, it is coordination compound. It contain metal magnesium. Hemoglobin, it is coordination compound. It contain iron. Similarly, vitamin B12, it is coordination compound. It contain cobalt. Okay, so here coordination compound means generally transition metals make bond with the neutral molecule or negatively charged species and form coordination compound. Okay, next one we have to discuss here Werners theory. Swiss chemist Alfred Werner formulated the structure of coordination compound. Alfred Werner formulated the structure of coordination compound. Also, Werner introduced two type of valency for coordination compound. Two type of valency, primary valency and secondary valency. Okay, so see here. The compound, this type of compounds, these are binary compound. This type of compounds are binary compounds. Binary compounds mean there are two different type of atom. Here chromium and chlorine. Here cobalt and chlorine. Palladium and chlorine. So here only two type of atoms. So this type of compounds are binary compounds. Binary compounds have only primary valency. This type of compounds, they have only primary valency. I told you before, Werner introduced two type of valency, primary valency and secondary valency. But this type of compounds, they have only primary valency. Here primary valency 3. Here 3 chlorine, so primary valency 3. And here primary valency 2. And here primary valency 2. Here 3 chlorine, primary valency 3, 2 chlorine, primary valency 2, 2 chlorine, primary valency 2. Okay, so there are two different type of valency, primary valency and secondary valency. Clear? Okay, next one, see here, we have here cobalt compound. We have coordination compounds which contain central metal ion cobalt. Also it contain chloride and ammonia. Okay, chlorine and ammonia. When this compound reacted with excess silver nitrate, silver chloride formed as a precipitate. These are the cobalt compound. It contains different amount of chlorine and NH3. When this compound reacted with excess amount of silver nitrate, it formed silver chloride as a precipitate. Okay, here the amount of precipitate, number of moles of precipitate formed in each case, it is different. See here, in first case, cobalt chloride reacted with 6NH3. It formed 3 moles of AgCl. Okay, it means 3 chlorine removed from here. 3 chlorine removed. Okay, so this 3 chlorine removed. Then it formed 1 cobalt and 6 NH3. See here in this compound, cobalt chloride 5 NH3 reacted with excess silver nitrate, 2 moles of AgCl formed. So here 2 chlorine removed. 2 chlorine removed. So still there is 1 chlorine and 5 NH3. 1 chlorine. See here, from this compound only chlorine is removed. NH3 is stable. NH3 constant, only chlorine removed. In this case 3 moles of chlorine removed. In this case 2 moles of chlorine removed. And here in this case 1 mole chlorine. So here 1 mole chlorine removed. Here it was 3 chlorine, it removed, and now it is 2 chlorine. So what you can observe here, during this experiment, see here cobalt and 6 NH3, and here cobalt, 5 NH3 and 1 chlorine, total 6. Okay, here 1 chlorine, 5 NH3, 1 plus 5, 6. Here cobalt and 6 NH3, here 6 NH3, and here 1 chlorine and 5 NH3, it is 6. And here 1 chlorine removed, now there is 2 chlorine. 2 chlorine and 5 NH3, so again it is 6. So here different coordination compounds of cobalt reacted with excess silver nitrate, it forms silver chloride as a precipitate. During this experiment, it was observed that here the atom or group which attached to cobalt, it is 6. Either chlorine or NH3, or both chlorine and NH3 together, it will be 6 group attaching to cobalt. You understand? Here during this experiment, it was observed that 6 group, there will be 6 group, 6 NH3 or chlorine and NH3 together 6. There must be 6 group attaching to cobalt. Okay, either NH3 or Cl minus together, there must be 6 group attaching to cobalt. Clear? So here from this experiment we can see here, you can check this table here the formation of positively charged ions and negatively charged ion, the ratio of positively charged ion and negatively charged ion. Look here 1 and here 3, so 1 is to 3. Also you can check the table, the ratio of positively charged ion and negatively charged ion, it will be 1 is to 3. Also here it will be 1 positively charged ion and here 2 chloride ion, so it will be 1 is to 2. And here it will be 1 positively charged ion and 1 chloride ion. Cl mean 1 chloride ion here. Okay, here 2 chloride ion, here 3 chloride ion. That's why here 1 is to 3, 1 is to 2. Here it will be 1 is to 1 because 1 AgCl. Okay, so this compound form 1 positively charged ion and it will release 3 moles of Cl minus ion. And here it will be 1 positively charged ion, 2 moles of Cl minus ion. Here 1 positively charged ion and 1 negatively charged ion. So the ratio will be according to this table, 1 is to 3, 1 is to 2, 1 is to 1. Clear? Okay, so see here next. Generally coordination compounds are represented like this. Okay, here the species inside this square bracket do not ionize after dissolving in the water. Okay, they form a single entity. Okay, they form a single ions after ionization. And here this group here it represents metal. Okay, metal ion. And here this is one of the group and this is another group. Here the group which inside the square bracket, it is directly bonded to metal ion and it is called secondary valency. The number of ligands or number of ions which bonded to metal ion directly, that is secondary valency, and it do not ionize after dissolving in the water. Clear? And here these are directly bonded to metal ion, and here the ions which the group which outside the square bracket, it depends on the primary valency depends on group which is outside the square bracket. Clear? Okay, next one we have to discuss here main postulates of Werners theory. So here these are the main postulates of Werners theory. Here first point saying in coordination compound, I told you before, we can represent a coordination compound like this. A coordination compounds which consist of two type of valency, primary valency and secondary valency. This is the first point. Okay, in a coordination compound there are two type of valency, or you can say two type of linkage, primary linkage and secondary linkage. Primary valency are satisfied by negatively charged ion. Okay, so this is primary valency, the group which attach, the groups present outside the square bracket, it is primary valency. This primary valency is satisfied by negatively charged ion. Primary valency are ionizable. Okay, primary valency, it is ionizable and it is satisfied by negatively charged ion. Next point here, secondary valency. Secondary valency, it is not ionizable. It is directly bonded to metal ion and it is not satisfied by, it is not ionizable. But secondary valency, it is satisfied by neutral molecule or negatively charged species. Okay, so here secondary valency, they are non-ionizable. Okay, and it is satisfied by neutral molecule or negatively charged ions. Clear? Next one here, secondary valency. Here this number of secondary valency, it is equal to coordination number. Okay, here two groups are inside the square bracket, so it's coordination number 2. So here number of secondary valency, it represent coordination number. Okay, and here the group which directly attached to central metal ion, this is secondary valency, and this secondary valency, they have characteristic spatial arrangement. They have three-dimensional arrangement in space. Okay, and this three-dimensional arrangement, it is called coordination polyhedra. It is called coordination polyhedra. So here we discussed here the ions or group which attached by secondary valency, they have spatial arrangement, they have characteristic spatial arrangement, they have three-dimensional arrangement, and this three-dimensional arrangement called coordination polyhedra. Okay, and here next point here, the species inside the square bracket, it is called coordination entity. The species inside the coordination sphere. Okay, this is this square bracket, it is called coordination sphere. Okay, so here species inside coordination sphere, it is called coordination entity, or you can say coordination complex. Okay, coordination complex or coordination entity. And the species outside the square bracket, it is called counter ion. Okay, counter ion means species outside the square bracket, it is called coordination entity. So here we discuss different points, main postulates of coordination, main postulates of Werners theory. First point here, all coordination complex, they have two different type of linkage or two different type of valency, primary valency and secondary valency. Okay, here primary valency, it is ionizable, okay, and it is satisfied by negatively charged ions. Secondary valency mean here group directly attached to central metal ion, it is not ionizable and it is satisfied by negatively charged ion or neutral molecule. Okay, and the group which attached to central metal ion, it is secondary valency and they have characteristic spatial arrangement, and this spatial arrangement, it is called coordination polyhedra. Okay, and here the species inside the coordination sphere, it is called coordination entity or coordination complex, and the species outside the coordination sphere, that is called counter ion. So these are the main postulates of Werners theory. Okay, also Alfred Werner explained the structure of coordination compound. Different type of structure, octahedral, tetrahedral, square planar, this type of structure. See here example, this type of compounds, here 6 ligands. Okay, here 6 ligands, here 2 plus 4, 6 ligands, and these compounds are octahedral in geometry, octahedral. Similarly here 4 ligands, here 4 ligands, coordination compounds, they are tetrahedral. Okay, here this type of atoms or group of atoms which directly attach to central metal atom, these groups are called ligands. Okay, and here 4 ligands attached to central metal atom, so here it is tetrahedral. Also here 4 ligands attached to central metal ion, so here it is square planar. Why it is tetrahedral and why it is square planar, this we will discuss later. Okay, so coordination compound which contains 6 ligands, octahedral, 4 ligands, 2 possibility, tetrahedral and square planar. Clear? Okay, next one we have to discuss here difference between double salt and coordination complex. Double salt and coordination complex difference. Okay, so here basically we have to understand both double salt and coordination complex are formed by mixing of two stable compound. After mixing two stable compound in a stoichiometric ratio, in a fixed ratio. Okay, there should be a fixed ratio during mixing of two stable compound. After mixing these two stable compound in a particular stoichiometric ratio, here both coordination compound and double salt are formed. But here we have to understand double salt, it will ionize completely in water. Double salt after dissolving in water completely ionize. Example for double salt, very important, double salt, more salt. FeSO4, NH4 twice SO4, 6H2O. This is more salt. More salt mean salt with it contains 6 water molecule. Another one, potash alum. Potash alum. Okay, KAlSO4 twice 6H2O. Here potassium aluminium sulfate. Okay, potash alum mean KAl, potassium aluminium sulfate with 12 water molecule. This is potash alum. These are example for double salt. Okay, but here coordination compound do not ionize completely after dissolving in water. It will not dissolve completely, or it will not ionize completely after dissolving in water. That is coordination compound. Example for coordination compound, see here FeCN6 4 minus K4 FeCN6. Okay, here potassium outside the coordination sphere. Okay, we will study more example this type of coordination compound. Clear? Okay, next one we have to understand here some basic terms which used in coordination chemistry. So see here, first one we have to understand here coordination entity. Coordination entity means central metal atom. Central metal atom or central metal ion. It is directly bonded to fixed number of group of atoms or different type of ions. Okay, this together it is called coordination entity. See here, this is central metal atom. It is directly bonded to different atoms or group of atoms. Okay, this together it is called coordination entity. Okay, so here coordination entity, it consists of central metal atom or metal ion. It is bonded to fixed number of ions or molecules. So that is coordination entity. Next one we have to understand here central metal atom or central metal ion. See here we discussed this is coordination entity. So here this is central metal atom. Okay, so central metal atom, this is central metal atom. So central metal atom or central metal ion mean metal or metal ion on which fixed number of atoms or group of atoms are directly bonded. Such type of metal or metal ion are called central metal atom. So see here, this is one example. Here nickel, here it is nickel 2 plus, and here cobalt 3 plus. Okay, and I will discuss with you later how to find charge of this central metal atom. Okay, so you understand here in this coordination compound this is metal ion, and here this is metal ion, central metal ion. Okay, in coordination compound this type of metals are called central metal ion. So here we discussed coordination entity and central metal ion. Clear? Okay, here next one we have to discuss here ligands. Ligands mean atoms or group of atoms. Atoms, group of atoms or ions. It is directly bonded to central metal ion. Such type of atoms or group of atoms or ions which are inside coordination entity. Such type of atoms or group of atoms or ions are called ligands. Okay, so here ligands mean ions or molecules. Ions or group of atoms. Group of atoms mean molecule. Okay, ions or molecules, it is directly bonded to metal. Okay, and it will be inside the coordination entity. This atom or group of atom will be inside coordination sphere. Such type of atoms or molecules are called ligands. Example for ligands, see here Cl minus, OH minus, NH3, H2O. Here it is ethylene diamine, CH2, each side there is NH2. This is ethylene diamine, protein. These are example for ligands. So ligands may be ion, this type of ions. Okay, ions or molecule, neutral molecules or large molecule or macromolecule. So ligands may be ions, molecules or large molecule or macromolecule. Example for ion Cl minus, OH minus. Example for molecule NH3, H2O. Here ethylene diamine, it is large molecule, and protein, it is macromolecule. So these are example for ligands. Here there are different type of ligands. Okay, so we can classify ligands: unidentate ligands, bidentate ligands, polydentate ligands. Unidentate ligands mean ligands which contain one donor atom. See here, actually ligands mean we have coordination compound mean there is central metal atom and there is ligands. For example, NH3. This is ligand. In nitrogen we know there is lone pair electron. This lone pair electron will donate electron pair to central metal atom and form coordinate bond. Okay, so here NH3, there is one donor atom. Here nitrogen, this is donor atom. So unidentate ligands mean ligands which contain one donor atom. Such type of ligands are called unidentate ligand. Example for unidentate ligand: Cl minus, H2O, NH3, OH minus. These are example for unidentate ligands. So what will be bidentate ligand? Bidentate ligand mean ligand which contain two donor atom. Two donor atom. For example, ethylene diamine. This is one large molecule we discussed here. It contains two nitrogen atom, two donor atom. So it is example for bidentate ligand. Bidentate ligand. Another example, C2O4. C2O4. C2O4 mean two carbon, okay, and COO. So there is two donor atom. Here two donor oxygen atom. Clear? So bidentate ligands mean ligands which contain two donor atom. Okay, they make bond with the central metal atom by two donor atom. Such type of ligands are called bidentate ligands. Example for bidentate ligands: ethylene diamine and oxalate. C2O4 called oxalate. Oxalate. Okay. Next one, polydentate ligands. Polydentate ligands mean ligands it contain several or many donor atom. Okay. So here polydentate ligands mean ligands it contain many donor atom. Okay, they will donate, they contain many donor atom and they donate electron pair to central metal atom. Clear? Such type of ligands are called polydentate ligand. Example for polydentate ligand, very good example, EDTA. EDTA, it is polydentate ligand. Polydentate ligands, ethylene diamine tetraacetate. EDTA mean ethylene diamine tetraacetate. This is ethylene diamine tetraacetate. Acetate. COO minus. This is acetate. Here 4 acetate. Tetraacetate. Okay. Ethylene diamine tetraacetate. So here we discuss ligands. Ligands mean ions or molecules. They directly bonded to central metal ion in coordination entity. It is called ligands. There are different type of ligands: unidentate ligands, bidentate ligands, polydentate ligands. Unidentate ligands it contain one donor atom and they donate electron pair to central metal atom. Example, Cl minus, H2O, NH3. These are unidentate ligands. Bidentate ligands it contain two donor atom. Example, ethylene diamine, oxalate. Polydentate ligands mean it contains several number of donor atom and they donate electron pair to central metal atom. Example for polydentate ligand, EDTA, ethylene diamine tetraacetate. There are different type of ligands. Ligands may be ions, molecules, large molecules or macromolecules. Clear? Okay, next one we have to discuss here ligands. Ligands mean bidentate ligands or polydentate ligands. Bi or polydentate ligands, they use their donor atom. Bidentate or polydentate ligands use their donor atom and donate electron pair to central metal atom and form a ring structure. You can see here one chelates. You can see here one chelates. Chelate mean here bidentate ligands or polydentate ligands. They donate electron pair. They use their donor atom, two or more donor atom, and they donate electron pair to a single central metal atom and form a ring structure. Such type of ring structures are called chelate. For example, you can see here copper, and here ethylene diamine. You know ethylene diamine, it is bidentate ligand. Ethylene diamine, it is bidentate ligands. It consists of two donor atoms. Both donor atom donate electron pair to a single metal atom and form a ring structure. This type of ring structures are called chelate. Okay. And here next one we have to understand here ambidentate ligands. Ambidentate ligands mean ligands which contain more than one donor atom. For example, NO2 minus mean here nitrogen can donate electron pair to central metal atom. Okay, such type of compounds are called nitro, or you can say nitrito-N. Nitrito-N mean here the ligand NO2, here nitrogen donate electron pair. Also here nitrito-O mean here same ligand NO2 minus, but here oxygen donate electron pair. Okay, so here same ligand, it can donate electron pair from different atoms. Such type of ligands are called ambidentate ligands. Another example is Cn minus. Here sulfur can donate electron pair to metal atom. Also nitrogen can donate electron pair to central metal atom. Such type of ligands are ambidentate ligands. So here ambidentate ligands mean ligands which ligate, or you can say ligands which make bond using two or more different atom. Ligands, it use two or more different atom to ligate to central metal atom. Okay, here example NO2, nitrogen and oxygen. Cn minus, here sulfur and nitrogen. Ligands which contain more than two donor atom, two or more, not more than two. Ligands which contain two or more than two donor atom. Such type of ligands are called ambidentate ligands. First we discuss here chelates. Chelates mean bi or polydentate ligands use their two or more donor atom and bind to a single metal ion and form a ring structure. Such type of ring structures are called chelates. Clear? Okay, next one we have to discuss here coordination number. Coordination number mean number of ligands or number of donor atoms which directly bonded to central metal atom or central metal ion. Such type of ligands or donor atoms are called coordination number. Coordination number mean number of ligands or number of donor atoms which directly bonded to central metal atom or central metal ion. Clear? So see here, this is one coordination compound. Here this is central metal atom. In this central metal atom, here 6 chlorine atom directly bonded. So here coordination number 6. Here nickel, here 4 NH3 molecules directly bonded to nickel. So here coordination number 4. Okay, and in this case, look here, this is one coordination compound. Here ligand C2O4 mean it is bidentate ligand. C2O4 mean it is bidentate ligand. There is two donor oxygen atom. Okay, so here C2O4. One C2O4, look here, we discussed before C2O4 2 minus, there is two donor atom, so it is bidentate ligands. So here 3 C2O4, 3C2O4 means, so 2 times 3, 6 donor atom. There will be 6 donor atom. Okay, so here coordination number will be 6. Clear? Look here, this example here, iron ethylene diamine. We know ethylene diamine means CH2, here NH2, here also NH2. So there is 2 donor atom, 2 nitrogen, 2 donor atom. So it is bidentate ligand. Similarly here 3, 1. Here, look here, ethylene diamine means CH2, CH2, NH2, NH2. Simply you can represent like this En. En means ethylene diamine. One ethylene diamine, there is 2 donor atom. Here 3 ethylene diamine. 3 ethylene diamine means 2 times 3, 6 donor atom. So here coordination number 6. Here coordination number 6. Here also coordination number 6. Okay. Look here, coordination number. Coordination number of complex. Coordination number depends on the number of sigma bond formed between ligands and central metal atom. Coordination number always depends on number of sigma bond formed between central metal atom and the ligand, and it independent of number of pi bond formed between ligand and central metal atom. Okay, so coordination number always depends on the pi bond formed between central metal atom and the ligand, and it independent of pi bond. It independent of pi bond formed between ligand and central metal atom. Clear? Okay, next one we have to discuss here coordination polyhedron. Coordination polyhedron means three-dimensional arrangement of different type of ligands. These ligands are directly attached to central metal atom. Okay, spatial arrangement of ligands. These ligands are directly attached to central metal atom or central metal ion. This arrangement called coordination polyhedron. Okay, and here after three-dimensional arrangement, this coordination compounds getting different geometry. For example, octahedral, tetrahedral, square planar, etc. Okay, see here 6 ligands, and here this arrangement will be octahedral arrangement, and here 4 ligands. In this case there are 4 ligands. If there are 4 ligands, there is 2 possibility for their arrangement, tetrahedral and square planar. Okay, and see here this type of geometry, this is tetrahedral and this is square planar. This type of arrangement, it is square planar, and this type of arrangement trigonal bipyramidal, and this is square pyramidal. Clear? So here spatial arrangement of ligands around central metal atom. These ligands are directly attached to central metal atom. This arrangement called coordination polyhedron. Okay, and here you have to understand here if there are 4 ligands, 2 possibility, tetrahedral, tetrahedral, square planar. If there are 6 ligands, octahedral. Okay, next one we have to discuss here oxidation number of central metal atom. Oxidation number of central metal atom. In coordination compound, central metal atom carries one charge. This charge is called oxidation number. The charge carried by central metal atom, this charge called oxidation number. Okay, see here one example. This is one example for coordination compound. Here copper and 4 cyano group. Okay, here you have to remember cyano, Cn means cyano, it has -1 charge. We will discuss more details about charges charges of coordination, charges of ligands. Here Cn mean cyano, and it has -1 charge. Okay, and here Cu mean copper. We can find the charge of copper like this. See here, we want to find charge of copper. It is unknown, so use x plus 4 times -1. Here 4 cyano group, 4 times -1 equal to -3. Here it is -3 minus, that's why here equal to -3. Okay, so x minus 4 equal to -3, so you will get x is equal to +1. X is equal to +1. So the charge of copper +1, copper 1. Okay, the charge of copper +1. So we will write it like this. Okay, so we will use Roman letter like this. We will use Roman letter to indicate charges of central metal atom. For example, positive +1 charge we will use like this, +2, +3. Okay, we will use Roman letter to represent charges of central metal atom. Here copper +1 charge. Okay, so we can find the charges of central metal atom like this using charges of ligands. Clear? After this we have to discuss here heteroleptic complex and homoleptic complex. Homoleptic complex and heteroleptic complex. Heteroleptic complex. See here one example, homoleptic complex example, this one. Here central metal atom, it is bonded to only one type of ligands. Central metal atom, it bonded to only one type of ligand, one type of donor atom. Such type of ligands are called homoleptic ligands. Homoleptic ligands means central metal atom bonded to one type of ligand, one type of donor atom, that is homoleptic complex. Heteroleptic complex mean here central metal atom bonded to different type of ligands, different type of donor atoms. Example here cobalt, this coordination compound, here two different type of ligands, NH3 and chlorine. Okay, so here two different type of ligands or two different type of donor atom. This type of ligands called heteroleptic complex. This type of coordination complex called heteroleptic complex. Clear? So here we discuss how to find charges of central metal atom. Also we discuss here homoleptic complex and heteroleptic complex. Clear? So these are the things we have to discuss in this video. You can review this video once again, so we can discuss rest of the part next video. So thank you for watching this channel.